Today I'm going to present on the paper titled A Language-Guided Bayesian Optimization for Efficient LoRa Hyperparameter Search. It was written by Kostik and Keist, and it was published this year at ICML. So the problem they want to solve is an optimal, efficient solution for automatically finding hyperparameters for LoRa. And despite the reason for this is because despite LoRa being a more efficient, resource efficient alternative to full fine tuning, it still remains expensive due to yeah, because you have to train it for every iteration, for every combination. And this is difficult for because the parameters are intertwined, complex, and it must vary by dataset and model. It and Standard Bayesian optimization often fails because it cannot. First, it cannot. It has a difficult time incorporating domain-aware knowledge, like how LoRa parameters influence one another. Also, because it's Bayesian optimization, uh, the it deals with continuous data. So, and because LoRa requires discrete structured data, there can be trouble there. So the main method that they propose is to use a pre-trained LLM to basically work as a mapper for mapping discrete to continuous. It converts the hyperparameter configurations and domain-aware prompts, which is in text, into continuous embeddings, and using that for deep kernel learning for Bayesian optimization. So their main contribution, this is the first framework that combine. Okay. So this is the first framework that combines LLM with Bayesian optimization that is specific to LoRa hyperparameter optimization. Uh, it introduces optimization methods that makes the whole thing more time and resource efficient. And their through their experiments they demonstrate broad generaliz generalizability across variants, different architectures, and different machine learning tasks. So to get a bit deeper, the problem with existing works, which includes black box optimizations, LoRa specific strategies, and LLM and other LLM enhanced Bayesian optimization methods. The problem with these is that first, they often fail to handle. They they simply fail to handle discrete and structured nature of LoRa parameters. And second, the surrogate models are often yield unreliable results when evaluation data is sparse because because there is a lack of mechanisms to incorporate domain-specific expert knowledge. So yeah, like I said, they combine LLM with BO for this task, and they do this by using domain-aware text templates and and a trainable projection layer to calibrate the embedding space. So how does it work? Like I said, LLM working as a discrete to continuous mapping module, uh, so that it leverages both the LLM's pre-trained knowledge as well as the learned calibrations. So so in the pipeline, first they fine-tune LoRa with specific set of configurations with only the 10% of the entire data set. This is actually one of their contributions as well. Uh, they fine-tune LoRa with only 10%, and which would yield their proxy performance score. And the configurations that were used here would then be converted into domain-aware text template and then combined with a learnable token psi and pass it through the frozen LLM and then a projection layer to create an embedding. And they would use this embedding and the performance score to the, uh, update the surrogate model by jointly optimizing its kernel parameters, the projection layer, and the learnable token. And then with that, they use an acquisition model, specifically expected improvement, to suggest the next configuration from the candidate pool. And then they would iterate this for a set number of times. They Because this entire task involves delving into the actual layers of the LLM, they must use an open source one, so they use Qwen. And so the architecture is a model LLM and then a projection layer, which consists of a linear layer, dropout, and ALU activation. The surrogate uses Matern kernel to model the performance distribution over the calibrated embedding space. So, like I said, prompting, then which is appended with this learnable token, which is meant to capture residual domain information not easily expressed in natural language, so that it helps with the embedding. It helps the embedding implicitly to implicitly internalize knowledge, LoRa specific knowledge. And then after the LLM, there's the projection layer calibrating the high dimensional LLM hidden states into a smooth discriminative feature space. Uh, and then you have the kernel and then the acquisition function. Yeah, loss functions, they use marginal log likelihood. They maximize for marginal log likelihood, specifically the kernel parameters, projection layer, and the learnable token. And for training strategy involves yeah, the LLM remains frozen. Only the projection layer and the learnable token are updated at every iteration. So three tasks: math, coding, and conversation. Uh, they were fine-tuned with these and then evaluated on these. And like I said, one of the contributions is demonstrating that fine-tuning LoRa with only 10% yields approximately the same results as training for the entire thing. So 10%. And these are the LoRa parameters. And the iterations were set to 30. And then these are the baselines, as well as this framework called Lambo, which uses LLM as a black box. And results show the best result that their model yielded is 21.46 accuracy improvement on the math task. But this as you can see there, it's not just for math, but for every task theirs performed better, and this trend did prove to be consistent across variants. And their results show that uh, yeah, one of the things that they discovered using their method is that optimal configurations often utilize higher ranks than what we used to consider standard baselines. And through their proposed method, they discovered that uh, apparently there's this rule that alpha should be twice the rank. But through their method, they discovered that the alpha is can be up to 16 or 32 times larger than the rank. So this is another major contribution that they discovered using one of their contributions. So ablation studies involve the domain-aware prompting and the projection layer, and their ablation studies prove that both are required, especially the domain-aware prompting. And qualitative results, here these are this is using just the LLM, the frozen LLM, and then this is with the what was it? Domain-aware prompting, and yeah, this is with the learnable token. And as you can see, with each component, the figure progressively becomes more aligned with this trajectory. The trajectory of the iterations become more aligned with the actual model improvements. So, and also, uh, principal component analysis showed basically that the primary direction of the calibrated embedding space effectively sorts hyperparameter configurations from worst to best. Basically, uh, yeah, it looks the thing is organized beautifully. Uh, failure cases. Uh, One thing that they learned through their experiments is that the configurations discovered for one model architecture does not is not the best for another architecture. Like meaning there needs to be different configurations for different model series. In other words, near optimal settings cannot be found for one model. There's no one fits best kind of set of configurations. So the strengths, computational efficiency, like I said, they use only 10% of the training data when they do proxy evaluation, the LoRA fine-tuning, which can reduce total optimization time by up to 10 times. Uh, Domain awareness, they map the discrete hyperparameter space with continuous optimization using text templates that can control domain structures. And hyperparameters, uh, they discover that hyperparameters discovered on smaller models remain highly effective when transferred over to larger versions. And this entire thing can be used as a plug and play module, which broadens their generalizability. Limitations, again, neural optimal settings are highly dependent on model architecture. So one configuration does not transfer to another architecture. Uh, and despite the improved efficiency, the whole thing still requires repeated cycles of fine-tuning, so it will require some resources. And as for this, because this is a fine-tuning paradigm, this could be used not just for LoRa, but for any domain task specific model, and which is one of their listed future works. But should that happen, there could be potential risk of misuse due to the fact that small errors in hyperparameter driven performance could lead to consequences. So for future work, like I said, broader fine-tuning strategy. Well, what I said is the paradigm being used for other complex fields, domain-specific one that requires domain-specific knowledge. Also, they list broader fine-tuning strategies for beyond just LoRa and perhaps future and another future work can be investigation into how different embedding LLM properties can influence the quality of learned hyperparameter representations. That's pretty much it for the paper. Do you have any questions?
They have given some information, the difference between um, time when they use optimization, it's Bayesian.
Yeah.
So without Bayesian and with Bayesian, I mean, it can
Mhm.
increase significantly training time.
Uh, well, the two of the baselines listed here are just random, and this
Up to now.
up to now, which uses some other algorithm, which I forget what it was called. It was some tree related
Okay.
optimization method. So those two that they did compare, others they did not.
Mm, it's just the accuracy. Oh, latency.
Latency, uh, I didn't bring the graph, but there's do prove to be significantly faster, more time efficient.
Oh, they haven't focused on the efficiency or not.
They did. I just didn't bring the figure.
Yeah, I appreciate it.
But like I said, because they use only 10% of the data to fine-tune LoRa for each optimization iteration, yeah, they
Mm.
are bound to be more time efficient.
In my understanding, they try to solve the problem that is a gap between the pre-trained one and the fine-tuning data. Fine-tuning training? I actually didn't understand
Well,
what they wanted to address.
the problem that they are solving is, uh,
Hyperparameter
yeah,
selection. Mm.
hyperparameter selection
They will
optimization.
take multiple combinations of multiple parameters,
Right,
I
right,
think,
right.
and then they will select best one or the optimum one.
Yes.
With a
This is for fine-tuning LoRa, finding the best hyperparameter for LoRa.
finding an optimum hyperparameter
Yeah.
with a what is the purpose of it? Frozen LLMs on there and
They're using the frozen LLM to map the discrete nature of the LoRa hyperparameters to the continuous data that is necessary for Bayesian optimization.
Ah, got it. Yes.
And using Bayesian optimization, using continuous data does allow the entire framework to find the optimal.
Yes, I finally got them.
On what basis the algorithm selected the optimum hyperparameters?
What basis?
On what basis?
Uh, they used this for evaluation. So they would optimize for these data sets. So they would optimize for each of these tasks.
Okay, reasoning, transformation, and conversation. Hmm.
And that's the whole expression of logician.
Yeah.
Correct.
If no other questions, thank you for listening.